If you watched my previous video about asynchronous code in Unity, you already know that UniTask is my go-to choice for async programming. But knowing which tool to use and knowing how to use it effectively are two completely different things. In this video, I'll walk you through how the compiler actually treats your async code, the common mistakes developers, including me, tend to make, and the best practices that make your async code cleaner, safer, and more efficient. Because without understanding what's going under the hood, it's easy to introduce unnecessary allocations, memory leaks, and even miss unhandled exceptions. So, let's get started. As always, I prefer installing my packages using the OpenUPM CLI, but you can use any other method you like. You'll find the available options on the UniTask GitHub page. I've added a link in the description. Before we dive into UniTask specifics, let's first understand what actually happens when you write async await code. When you mark a method as async, the C# compiler doesn't just leave your code as is. It performs a transformation that completely restructures your method behind the scenes. Let me show you a simple example. Here's a basic async method that waits for 1 second and then returns a random float. But this isn't what actually runs. The compiler generates something called a state machine, a complex structure that manages the execution flow of your async code. Thankfully, Rider has all the tools to show you what it looks like. First, I need to build the project. And now we can view the generated code. Here you can see the IL code, but I can also switch it to a low-level C# view. What you see here isn't pretty, but this is exactly how your code looks once all the syntactic sugar is stripped away. As I select different parts of the code, you can see their counterparts highlighted in the IL viewer. Notice how the async keyword disappears and our simple 2 lines of code turn into something much more complicated? A new state machine instance with several properties being set. If I highlight the delay method, you'll see the IL viewer jump way down in the moveNext method of the state machine class. Random.range sits in another branch entirely. Now, if I add another await and rebuild the project, you'll see the state machine grow, adding another awaiter and more logical branches. This entire state machine is a class, and every call to this async method allocates memory that later has to be cleaned up by the GC. But here's the good news. Sometimes we can actually avoid state machine allocations. There are cases when we need to execute some synchronous code first and then run async operation. One way to do that is the way we just did, write a log and then return the result of an awaited method. But if I compile this and look at the generated code, you'll notice that we now have 2 different state machines. By invoking log and get random, we've essentially doubled our allocations. In this case, though, we can easily fix it. We can simply remove the async and await keywords. If I build it now, you'll see we've gotten rid of the second state machine, and the log and get random method is almost unchanged. Now, if you're seeing this for the first time, you might be wondering, what happens to async code if you remove those keywords? Does it become synchronous? The answer is no. Async and await are just syntactic sugar that the compiler uses to generate the state machine. The actual async behavior happens inside the task, or in our case, the UniTask. All the async logic is already there. The method itself doesn't magically execute. The caller is the one that awaits it. And that chain of tasks can be really long, but somewhere it's still going to be awaited. This is nice. However, this approach only works if we just want to log before the task starts. If we try to log the random number after it's calculated, this trick won't work. Because when we log it, the random number doesn't exist yet. It's still waiting for 1 second before being generated. So in that case, we have to await. There are also cases when you need to write synchronous code inside a method that returns a task. For example, when implementing an interface that requires that signature, but you don't actually need any async behavior. Let's say you just want to log the execution. This code won't compile, because the compiler expects a UniTask as the return value. And what I often see developers do is add the async keyword. But as we just saw, that's not ideal because it creates a new state machine instance. The proper solution in situations like this is to use UniTask.completed_task field. That way, we avoid unnecessary allocations entirely. And by the way, if you need to return a value, you can use UniTaskFromResult method. Just pass in the value you want and it'll return a UniTask that already contains it. No need to waste resources on state machines. Sometimes you want to start an async operation, but you don't want to wait for it to complete. Let's say you have an object that's supposed to move slightly when it spawns. Putting that logic inside update would mean running a useless check every frame after the movement is already done and not required anymore. So instead, we'll create an async method. I'll write a log before the method invocation, and then another one after we invoke this method. Let's see how it looks in Unity. For simplicity, I'll create an empty image on the canvas and attach the fire and forget script to it. When I hit play, the image moves upward for 3 seconds and then stops. Now, let's run it again and look at the logs. As you can see, the move completed message from inside the task appears after the move object called log. This pattern is called fire and forget. You start the operation and don't wait for it to finish. But there's a problem. If you call an async method without awaiting it, the compiler gives you a warning. And for good reason. If that async method throws an exception, no one will catch it. Let's simulate that. I'll add an exception inside the async method. But keep in mind, this could just as easily be a null reference exception, an index out of range, or anything else. I'll wrap it in a try-catch block and log the exception. I'll go ahead and run the code one more time. Now, the image doesn't move. The code crashes, but notice no error logs appear, even though surrounding logs still work fine. That's because the code inside async method runs asynchronously, while the flow that coded runs synchronously. One common mistake is to switch the method to async void. It removes the warning, but exceptions inside can't be caught by the caller, or by anyone. Let's see what that looks like. Now, we do see an exception log, but it's not the one we wrote. It's coming from Unity's synchronization context, and we can't handle it. So how do we handle this properly? There are two main options. You could wrap the code inside the async void with a try-catch block, but if it calls another async void inside, you won't be able to catch those exceptions either. The right way with UniTask is to use the forget extension method. Let me just remove the try-catch block, and then I can add the forget extension method to the move object call, and notice the warning disappears. That's because we're now explicitly handling the return task. Under the hood, forget safely manages the operation and handles any exceptions through a global exception handler you can configure. Let's set one up. For this example, I'll just log the error. But in a real project, you could report it to your analytics service or trigger a recovery flow or anything. Just remember to unsubscribe from the event when it's no longer needed. Let's head back to Unity and see it in play mode. And there it is, the error log we expected. The flow still continues uninterrupted. That's the nature of fire and forget tasks. But now at least we have proper control over exceptions. Now, there's one situation where you can't use UniTask with forget, and that's Unity event callbacks. When Unity calls a method from a UI button click, an animation event, or any other built-in event system, it expects either a regular void method or an async void. You can't make those methods return a UniTask because Unity simply doesn't know what to do with that return value. The solution is simple. Create a regular non-async void method, and inside it, trigger your async logic using UniTask with forget. But what if you actually want to create an async method that can't be awaited? Something you intentionally don't want anyone to await, like a true fire and forget operation. That's where UniTaskVoid comes in. UniTaskVoid is a special, non-awaitable return type that behaves like async void, but it routes exceptions through UniTask's global error handling system. It also does everything that forget does internally. In fact, if you look inside the forget method itself, it's basically empty. So why does it exist? Mainly to silence compiler warnings and to make your intent crystal clear. You're explicitly saying this method is not awaited on purpose. One of the most important aspects of async code is being able to cancel operations. Let's increase the duration of our movement animation to 30 seconds and remove the exception we had before. Now, imagine a scenario where we want to stop this animation halfway through. How can we do that? In C#, we have cancellation tokens, and you should always use them in your async code. There are many ways to work with them, but I'll cover only the basics here. To create one, you'll need a cancellation token source. And our movement method should receive a cancellation token as a parameter. Since cancellation token is a mutable struct, its default value is a non-cancelable token, meaning it's safe to use without any null checks. Next, we need to interrupt our operation when a cancellation is requested. We have two main ways to do that. Option 1, the quiet way. Just check if cancellation is requested, log that, and break out of the loop. Option 2, throw an operation cancelled exception in a one-liner from the cancellation token. Internally, this method does the same thing, but it also throws an exception when cancellation is triggered. Just note, operation cancelled exception is ignored by UniTask's global exception handler, so in a fire and forget method, you won't see a log for it. Now let's pass our cancellation token to the method. I'll remove the start method so it doesn't interfere with the animation. And inside the button click method, I'll create a new instance of cancellation token source and pass its token to the movement method. One quick note, this implementation isn't safe yet. If you click the button multiple times, it'll override the source and break the code. But that's outside the scope of this video. Finally, we'll add another button to cancel the animation. Now, let's set it up in Unity. Let's set up the button we created earlier. I'll change the text to start and assign the start method as its callback. Now I can duplicate the button. This will be our cancel button. I'll just update its text, adjust its position, and assign the cancel method to its onClick callback. Now let's run it. When I press start, the image begins to move. It'll keep moving for 30 seconds or until I stop it. And the moment I press cancel, the image stops instantly. But there's another issue here. Let's restart the movement. And this time, I'll delete the image object from the hierarchy while it's moving. And what's this? An unhandled exception? Unlike coroutines, tasks and unitasks aren't tied to game objects. They'll keep running even after the object is destroyed. So in this case, we're trying to animate something that is no longer exists. And that's naturally throws an exception. Luckily, there's an easy fix for it. All we have to do now is create a linked token source. Every game object already comes with a cancellation token that's automatically triggered when that game object is destroyed. So we can link our own token to it. That way, if the object gets destroyed, our async operation will be cancelled too. And while we're at it, let's also handle the case where the game exits. There's a built-in exit cancellation token that's triggered when the application quits, or in the editor when we exit play mode. Let's see it in action one last time. When I hit start, the image starts moving. If I press cancel, it stops immediately. And now, if I restart the movement and delete the image from the hierarchy, no errors this time. Everything works exactly as expected. Sometimes you need to create an async operation that doesn't fit the standard pattern. Maybe you're wrapping a callback-based API, waiting for a specific event, or implementing a custom async process. Let's say we have a simple UI pop-up and its show and hide methods are extremely straightforward. They just toggle the active state of the game object. But what if we want a method that shows the pop-up and then waits for it to close? With a UniTaskCompletionSource, we can turn almost any flow into an async method. First, I'll create the completion source. And just like before, I want to note, this approach isn't completely safe as is. In your actual code, you should handle multiple simultaneous accesses to the same async method. If you're not sure how, I have a short video about Semaphore Slim that might help. There's a link in the description. Next, I'll trigger the show method and return the task from the completion source. To mark the task as completed, I'll set the result inside the hide method. This will work fine. But remember what I said earlier about cancellation tokens? We should always use them. With one extra line, we can tell the cancellation token to cancel the completion source if its state changes to cancel. And finally, if our object gets destroyed, we should also notify anyone who's waiting for the operation. So I'll simply cancel the task inside the onDestroy method. Now let's create a class and call it, I don't know, a pop-up manager that uses this method. First, I'll add a reference to our pop-up. Then I'll create an async fire and forget method called showPopUp. Inside the try block, I'll log that the pop-up is being shown. Then call the showAndWait method, and once it's closed, I'll log that the pop-up was closed by the user. Notice that I'm also passing a cancellation token. This way, if the manager gets destroyed, the running task won't be left hanging. Inside the catch block, I'll handle only cancellation exceptions and log that the operation was cancelled for some reason. Finally, the last step is to actually trigger the showPopUp method inside the start. Let's create a simplistic representation of a pop-up in Unity, programmer art style. I'll start by adding a big image. We can all imagine it contains something super important. Then I'll attach the pop-up component to it. Next, I'll add a close button and place it in the top right corner where close buttons usually live, unless you're on a Mac. Now I'll assign the hide method to the button's onClick event. And that's it! Our super handy pop-up is ready. I'll just disable it so it starts hidden. Now for the manager. I'll create an empty game object, add the pop-up manager component to it, and drag our pop-up into its reference field. Let's hit play. When the game starts, the pop-up appears automatically, and you can see the log confirming that. When I click the close button, the image hides, and we get another log saying the pop-up was closed. Now, let's restart play mode to start over. This time, instead of closing the pop-up properly, I'll delete its game object from the hierarchy. And there we go, another log appears saying the operation was cancelled. No errors, no tasks left hanging, everything is clean and safe. The last thing I wanted to show you is composition. Often, you need to coordinate multiple async operations. Maybe you want to wait for several downloads to complete before proceeding. Or maybe you want to raise two operations and use whichever finishes first. UniTask provides powerful composition methods for these scenarios. First, let's assume we have a method that downloads a texture from somewhere. In my case, it's just a dummy method that waits 1 second and returns null. If we want to download multiple textures, we can naively do this, a for each loop where we await every download. The issue here is that the whole operation will take around 3 seconds, since we're waiting 1 second for each download. But our hardware can do much more. It can actually handle multiple downloads at the same time. Of course, we can turn each method call into a fire and forget operation by removing the await keyword. But then, we wouldn't know when everything has finished. Instead, we can aggregate all the tasks into a single collection and pass this collection to UniTask.WhenAll. This method runs all the tasks simultaneously and completes only when all of them are finished. If we don't care about every task and only want to wait for the first one to complete, we can use UniTaskWhenAny. It returns as soon as one of the tasks is done. And if we want to do something with the return value of each task, first we'll need to change the collection type to a list of unitasks with a return value. In our case, texture. Now we have two options. We can go back to UniTaskWhenAll, await all the tasks, collect their results into a variable, and then we can iterate through that collection. This approach is great if you only want to process everything once all results are ready. If you want to start all the tasks at once and react to each one as soon as it finishes, you can use UniTaskWhenEach. It uses a C#9 syntax that allows a wait for each. This way, every task that completes is handled immediately inside the loop. And that's async development with UniTasks in depth. As with most topics on this channel, it's impossible to fit everything into one video. So I try to cover as much as I can, hoping it sparks your curiosity and encourages you to keep learning. Maybe I'll do a follow-up someday, who knows? The key takeaway: async programming is powerful, but to use it effectively, you need to understand what's happening under the hood. If you want to see more Unity content like this, hit subscribe. And if you have questions about UniTasks or async programming, drop them in the comments below. Keep on creating, and I'll see you in the next one.